It's my pleasure today to introduce Tyler Sutterley. I was lucky enough to have Tyler as he worked with me during his PhD, and he graduated in 2016. After graduating, he went for an MPP postdoc. It became an MPP postdoctoral fellow at Garris Place Center, and from 2017 to 2019. In 2019, he moved as a research associate to the UW, University of Washington Applied Physics Lab Polar Science Center. In 2021, he became senior research scientist, and last year he was elected PI council member of the Polar Science Center at UW-APL. And we started working on GRACE, but one of the things for which at present Tyler is most recognized is that one of the lead experts in utilization and science related to the ISAT-2 satellite mission, while it's still maintaining a very lot of work done for GRACE and GRACE follow-on. And he has developed a multi-stereo system to process together different airborne and satellite altimetry data. He led work on ice shelf tile grounding zone mapping and ice shelf flexor using ISAT data. He has led and coordinated work on Greenland and Antarctica surface mass balance and firm model evaluation with ISAT data, ISAT-2 data. And he is one of the developer and advisor of the ISAT-2 SlideRule project, which he's going to talk about today. And so it's my pleasure, and I think that everybody that uses altimetry in the community or use ISAT knows Tyler, because he's one of the key go-to person to. And would no further go, and not just for eyes, all application of altimetry data.
Yeah, thanks. It's weird to be back in this room. The screens are nice. Before it was projectors and everything kind of bleached out. These screens are pretty nice. Yeah, I'm Tyler. I'm from the University of Washington, and I'm here to present on SlideRule, which is a project that I have been a member of for the past 3 years. To start out, let's talk about, hopefully, maybe we won't. Maybe we'll be done and we'll have one slide.
You have to go describe everything. Okay, I'm gonna grab.
Well,
You can keep.
I have a cool laser though. So I have like a tiny ISAT-2 almost. Anywho, let's see if I can do it from this direction. Do it that way. I can do it that way and it'll be manual. Then I'll just do it this way. So ISAT-2 is a laser altimeter. It's one of NASA's next generation laser altimeters. It was launched in 2018. It consists of I think we're good.
Yeah, there we go.
Oh, remote's working too. Perfect. Consists of a single laser that fires and is split into 6 beams. These 6 beams we pair up into 3 beam pairs, and each beam pair consists of a strong beam and a weak beam, with a strong beam being roughly 4 times as powerful per shot as a weak beam is. We separate these beam pairs by 3 kilometers each. The separation of 3 kilometers is to gain spatial coverage, which is important particularly for our forest mapping objectives. And then each beam pair is separated by 90 meters. The 90-meter separation is to instantaneously calculate what the surface slope is, which was a problem with the original ISAT mission, which was only what we call nadir looking. It only fired a laser straight down to the ground. And so you got to measure a bunch of times to try and figure out what the slope was. ISAT-2 is what we call photon counting. Every laser shot fires about 100 trillion photons, and about 10 of them return to the satellite. And we stack all these photons together to create a product that you can measure about every 70 centimeters long track. This is our very special detectors where we can, for every single photon, get latitude, longitude, time, and height. And so I liked a kind of a metaphor that Francois just said, it's like a Xerox machine. We're scanning the planet with these lasers. And we are using this for ice applications, forest applications, and a bunch of applications are becoming more and more apparent, such as ocean bathymetry and lake surface topography. I said there was a bunch of products. It's always overwhelming to look at this, but it's everywhere from photons, where we have the individual photons, which is a product we call ATL03, to grid products, which are more comfortable for people that are in modeling applications. Today we're going to talk about 3 products, which is ATL03, the global geolocated photon product, ATL06, which is a land ice product, and ATL08, which is land and vegetation product. ATL03 is the big one. It's a data set that's over 300 terabytes. It gives us, again, lat, long, time, and elevation for every photon that returns to the satellite. There's a lot of work to try and figure out, is this an actual signal photon, or is this just a random green photon that entered the telescope? There's a bunch of corrections for tides, both solid earth and ocean. They're going to it. Instrument parameters, such as delay times. And this one's important because everything's there. All the products down from there, from the LandX product, the grid products, are derived from this single photon one. But it's huge, and it's unwieldy, and it's very hard to look at. It's important because, like I said, you can make everything from it, and so if you want to do something that the scientists who designed the original products didn't keep in mind when they first designed these things, you want to go first back to first principles at ATL03. But you look at these things and it's just a complicated flood and a mess of whatever now you're looking at. The purple here is what we think of as high confidence. This is near Thwaites Glacier in Antarctica. So we have a band of high signal photons, but then we have a bunch of photons that are related to it being a green light. And so there's a solar. We have this thing that's called TEP, which is an instrument set of photons, not real signal. And then we have thick clouds. And so if you're trying to measure height, you have a lot of data that's just not important to you. And so that's why this can blow up fast, is you're having 300 terabytes of data, but a lot of it can be background. ATL06 is the product that we put together for land ice. It fits a surface every 20 meters, and this surface is 40 meters in length. This gives us surface slope, latitude, longitude, and height. It's a lot smaller product. It's much easier to work with, but it could be a little bit too coarse if you're wanting to look at crevasses. It also only fits a single surface, so if you're wanting to look at lake, superglacier lake top and bottom, you're only going to have this measurement for one of them. And we're not sure which one it'll be because it's kind of random based on the thickness of the ice on top. In some cases, 40 meters is too fine. You might be looking at the interior of Antarctica and it's like, I don't need 40 meters. This is the most boring place on the planet. But if you want to make repeatable measurements, this is typically where you go if you want to do land ice. This is sort of what it looks like plotted on top of a bunch of photons zoomed really far in. You have a bunch of segments, a bunch of lines on what the surface slope is, fit from those photons. ATL06, I forgot to mention this, also has a bunch of corrections to get sub-centimeter level precision, which is not what you would find with ATL03. But you need to be able to take an average of these photons to figure out what those corrections are due to the actual shape of the transmitting pulse not being purely Gaussian. ATL08 is the land vegetation product. It's a lot of text. I know I've been just hammering you with text. It's a lighter product. It's really cool as you can not just have a single surface, you can have ground, canopy heights, or float around, ground, lake bottom. And ATL03 or ATL08 is also nice as they give you what they think each of these photons are. So it's like if they think this is the top of a canopy photon, ATL08 can tell you, hey, I think this is the top of the canopy. But if you're in heavily sloped areas, ATL08 breaks down. So what if you want to do something different? That's where we came up with SlideRule, which is a collaboration between where I used to work at Mass Goddard and where I work now. at UW. SlideRule is an open source project, and it is meant to try and make processing 803 simple and easy. It's an unwieldy product, but we're trying to make it so anyone, including myself on my phone, as I was showing Isabel a little bit ago, you can do it on your phone. It's a simple product to use, and it's a way of trying to think of, instead of you going and getting data files from NASA data server, having this data come to you directly. It's sort of a data as a service model. And the hope is that we made this applicable and easy for anyone to use, and you can just use it in your day-to-day. The main thing here, this is a service of you as a researcher, you know what you want to do. You know where you want to process the data, and you get to choose how you want the data to be processed, and we're giving you a quick and easy way. And we're not talking about like okay, I submit a job and I can go, home. We're talking about tens of seconds, maybe a minute or two. And so it's a way of trying to get all this data processed in a way that's quick, and so you don't have to worry about it, it just is delivered to you. This is the team. At the very top is Tom Newman, who was my postdoc advisor at Goddard. I'm kind of in the middle. Our data science lead, or our science lead at UW is David Sheen. Our software development lead is JP Swinsky at Goddard. And then the ASAS lead, that's guy who wrote all the actual Fortran code to make the original data product, is Jeff Lee at Polis. So how does SlideRule work? In a very simple way, there's you in green, you're behind the Jupyter notebook, and you make a call to SlideRule, and SlideRule accesses the data from S3, which is now being provided by NSIC on S3. In order to figure out what data you want to process, we use NASA's Common Metadata Repository, or CMR. CMR is where NASA has information on every single Earth science data product that they host. And so if you want to find when and where and how much data is at any given place, you query CMR. And it's sort of the backbone of a lot of science applications. If you do Earth data science search at NASA or at NSIC, it's querying CMR in the background. The more complicated plot, still with you in green on the left, but you can also now be in a web browser, is that you are accessing SlideRule, which is in a elastic compute node, or EC2. And there you are still accessing data from S3, but there's more things. So all of our website and our documentation and our provisioning system, so that we can provide compute nodes to you, that's all in what are known as serverless computing, or like Docker containers, if you like Docker. Who doesn't, I guess? But the main thing is you can do everything either behind a web server using like our web demo, or through Jupyter notebooks. We had a bunch of requirements that we started with this. We wanted to be cheap so that it can scale up, it can scale down, and shut itself down so that we're not accruing a bunch of costs. And in this way, we're trying to make cloud computing easy. Some of the big barriers to people using cloud computing is it's very easy to rack up a bunch of costs by just leaving your servers up. So we wanted it to go up and scale down based on use. We also wanted, like I said, we wanted this data to be returned to you as fast as possible. So a lot of work went into optimizing the reads of these granules so that you can get data in tens of seconds versus minutes or hours. We also wanted to make it easy to install. For people that are familiar with Python, it's a quick, common install. You can also use the web demo where you don't even need to have Python. You can just go on a website and look at it. As opposed to NASA data products, which goes through for ISI2 a 6 to 8 month update cycle, we make continuous updates all the time. And so if something goes down and we want to add new features, we are making those all the time. And so we were kind of a quick way of testing future features that are going into data products, and also testing things out of what researchers want to do. And the main thing is to enable the ability of you guys to do what you want to do as fast and easy as possible, and make science quality algorithms. These are the algorithms that make products available to you as scientists. So if we go back, step back, HLO3 starts with photons, a bunch of them. And the way you go from HLO3 to HLO6 is that we have this iterative surface fit, where we start with a big window and we iterate smaller, 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 until we think we capture a window of photons that is signal and get the entire transmit pulse, or the reflected pulse in there. It's really good at capturing the small scale topography, but right now in SlideRule, where the original HLO6 has these sub-centimeter corrections, we're not doing those yet. That is some future work. But the surface fit that is in the original data product, we have that algorithm in SlideRule. So, bunch of words, bunch of plots, bunch of weird things. How do I use this thing? This is screenshots from Jupyter Notebook. You have little toggles of what you want, so you can classify how you want the photon to be, how you want to determine if there's signal, if you want only ones that are vegetation, if you only want ones that are ground. You can determine how long you want that segment to be. The default is 40 meters, which is the same as the land ice product, but you can make it smaller. You can get finer resolution if you want to look at things like crevasses. And since ICEIQ is nearly global, it goes from 88 north to 88 south, you can start anywhere. So I chose here, the most scientifically interesting place on the planet. It's Irvine. I did a return, and I got some data. ICEIQ over land areas is trying to get a full vegetation map, so it's not repeating the same spot every time like it does at land ice. It's off-tilting a little bit through time. So we don't have a whole lot of data. It's apparently not the most interesting place on the planet with ICEIQ, but I still thought it was interesting when I zoomed in with these interactive maps. Like, okay, you know, the reserve is a little bit further down, Union Hills is a little bit further up. I was really hoping we could bullseye the park, but we didn't. So, win some, lose some. So I chose a maybe more interesting place. So, this is Jacques Shop in Israel, sideways. Same thing, I drew a box, polygon around the ice front. And then I ran SlideRule, and we got a lot more returns as we're further north. You can kind of see, compared to this Arctic dim background, that it's out a little bit. The front is retreated a little bit as it's more purple than where the ice front was at point, but apparently there's nothing with the comments. With SlideRule, you can also click on one of these tracks and figure out what the time series is. And so that's what I did. I clicked on one of those tracks along the ice front, and this is what is happening at the shop in Israel. And again, this took minutes. Wasn't any thought, just something that I did because I was bored. And so you can see Yagershop and Finn, tens of meters over the ICEIQ time series. We start looking at repeat tracks in a quick, easy way. And this is stuff that anyone could do. And there's a bunch of applications that is opened up by SlideRule. One of them is terrestrial snow. The reason this SlideRule is important here is the original land and vegetation product doesn't work great over heavily sloped regions. But the land ice product isn't, at least at the time, run over land. It's a run over land ice. So this sort of product didn't exist. It also was too coarse to match HLO6 with DENs. And so there was no way of going from snow off to snow on really well. So it took Besso a long time until we got SlideRule to a point where it was operational for to use this to create these global capability of creating snow maps. Going for snow on or snow off to snow on, comparing a digital elevation model of the ground with measurements of snow. And it works actually really well. There's 2 stations that are called snow sites. This is in Grand Mesa, Colorado, And there's 2 snow-tilt sites where it compares really well with measurements from SlideRule, which is really cool. Here's over entire basins. This is Tuolumne watershed up in Northern California, and then the Newfound Valley in Washington. And you can measure snow off, you can measure snow on. So basically, if you look at those histogram plots, you have about 1 meter-ish of snow in Tuolumne and about ½ meter of snow in Washington. So it's an application that was unlocked just because we took algorithms and enabled people to use them. Another one is icebergs, and this is the largest SlideRule run. They basically created an entire Antarctic product at much higher resolution in order to get icebergs. This didn't work with the original product because we only ran over land ice. We didn't run over the ocean. And so if you want icebergs from IceSat 2, this is the way to do it. There is a sea ice product, but the sea ice product doesn't want icebergs. They cap the maximum height available because it messes with their algorithm to try and get sea ice. And so this was a way of creating an entire archive of where icebergs have been during the IceSat 2 period, and a quick, easy way to do it. The plot kind of in the middle is if you looked at an iceberg that was close enough to the grounded ice to where we actually took a measurement of it, and we did really bad. Sorry. And then the other thing that you can do is crevasses. 40 meters is too coarse to try and get the shape of rough surfaces and rough crevasses. And so with SlideRule, you can up the long track distance to be, say, 10 meters and measure the full shape of the topography. And you can tune, again, like what you want photons to be, signal or not signal, to try and really get your science application. And there's a bunch of stuff we're adding. So new things is, if you want to query particular elevation models from the Polar Geospatial Center, we now have it where you can feed in points and get measurements of points from Arctic and REMA. We're adding in new laser altimeters, including JEDI. JEDI is affixed to the International Space Station, but it provides a swath of measurements all towards more mid-latitudes. We're making a new land and vegetation product in collaboration with the original authors of the land and vegetation product, Amy Nunchwaner and Eric Gunther from UT. We're doing DM code registrations, and we're adding in these new sub-centimeter corrections for IceSat 2 so that you can do analysis where those corrections become important. So, to sum up on SlideRule. This is made for you guys. It's made for scientists and made for users in order to get stuff done fast, in an open way, and we try to be responsive enough to where if you have a problem, we make it work. It's all on GitHub, and we try to be quick on responses to issues or pull requests, adding features, adding capabilities, and keeping up and maintained as long as possible. And the importance of this being open science is this is the year of open science. Congratulations, we made it. One of these things for open science on the NASA side is TOPS, the transition to open science. There are several new calls to try and open all up as scientists. The importance of open source science and open science in general is, from a NASA side, that it accelerates learning, accelerates use of data products, such as a lot more people can use HL03 with SlideRule than if you try to download 340 terabytes on your local machine. Tom Newman wanted to know how many 5 gigabyte drives you would need, and it was something about 70 drives, that's what it is. So if you did everything by SneakerNet, we could send a few boxes of 5 terabyte drives to get you HL03, but you have to connect them all to your computer. TOPS is also providing materials for workshops and seminar series. We're going to have a seminar series for cloud computing and SlideRule in a few months. And there's also going to be a hack week, another hack week coming up. Again, the importance for funding agencies like NASA is they want people to use their data. And so you being an open source scientist enables more people to use data, and that makes NASA happy. And also for the general public means that, hey, I can look up how this was actually done. And so I can trust what was done because I can see what was done. You can improve public policy because you increase transparency and the trustworthiness of the science that you do. For scientists, being in an open source realm is in some ways very positive. You can expand your work and the visibility of your work through initiatives that like producing code, documentation, services. It's scary. You know, you spend so much time working on something, and then it's like, okay, well, someone to see all the warts in my code. So it's definitely scary, but it's a way of working in a collaborative way and in a way that is important for the future, without just in a more traditional model of only focusing on the papers that you publish. Papers are all obviously very important, and I think that they need to be put in open journals, but science is about moving, society forward. And so if you can enable new science by putting your work out there, then you're making everything easier for everybody. NASA sort of thinks itself in the middle, not fully closed, not fully open, but they're trying to transition more towards open by working for people to put their code out there, put their work out there, publish in open journals, and try to establish a culture that's less siloed and more collaborative. And with SlideRule, for me personally, it's been a nice opportunity as I got to be a part of the Iceberg project, which I wouldn't have done if I hadn't written tag codes and helped run SlideRule. And so it enabled me to be part of science that I wouldn't have been part of if we hadn't, tried to move things into an open realm. All right, almost there, guys. Headquarters is also starting to mandate, please be open to science, as they want adoption of their mission data. ISAC2 Science Team is sort of a model on that. There's open data sharing between team members. We present a lot of Jupyter notebooks on meetings, and there are hack weeks. Hack weeks are a fun opportunity for researchers, grad students, postdocs, early career, late career, anyone can come. And for a week, we just sort of work on little projects together. And there's teaching from ISAC2 experts, from headquarters on down, on getting stuff done. And it's a really fun time. And if you want to look at ISAC2 work, you can go on GitHub and find a bunch of repositories, including SlideRule. So this was one more thing of, this is that over Larson B, and drew a little polygon and let it work, and that's what Larson B looks like in ISAC2. Open science initiatives that ISAC2 is also hosting is also CryoCloud, which is between TOPS and the ISAC2 Project Science Office. This is Jupyter notebooks that are hosted for you guys in order to start working and moving your work from on-premises to the cloud. And so if you want to be able to work with cloud-hosted data, CryoCloud is a great spot to start. It's managed. There's a higher person at 2I2C to make sure that costs are maintained. And it's led by Tosh Snow and Matt Siegfried at Colorado School of Mines. There's going to be a workshop on CryoCloud coming up. We're just putting in the work for that. And like I said, there's going to be another hack week coming up in August, 7th through 11th. And so you might see on prior list or other listservs that we'll be hoping to invite you guys. They're a really nice and collaborative environment, and hoping that everyone learns something and gets along and can treat together in a nice collaborative way. And with that, thanks.
Thank you, Tyler. And I'm gonna ask you if you can, when someone asks you a question, if you can repeat it, maybe.
Yeah.
So for the Zoom, for the people. And
this is just a goofy question, but do you know what NASA's paying for hosting ISAT-2?
That is through NSIDC and an agreement between NSIDC and AWS. It's not cheap. The particular thing is, yes, the hosting, but also NASA is making it free egress. So grabbing it out of S3 and downloading it is a big cost. I don't have a number, but I know it's big.
It's free.
Yes. Yeah, so as long as you are registered as a NASA data user, which you don't have to be a scientist or you can be anyone, you can grab NASA data off of S3 for free. And so there's a definite cost. I have no idea the order of magnitude, but it's not small.
any other question? Sue?
I have a dumb ISAT question. So you have the two beams, the weakness as well. So it looked like the weakness for something like canopy height and the strong would be for soil height. Is that the idea of the two beams? Or?
The idea of the two beams is to have a radiometric difference for the detectors. And the main thing is, this was largely for land ice. If your surface is sloped, you want to be able to measure at two spots so you can figure out the slope instantaneously. With prior laser altimeters, if the surface was sloping, we measured here 1 year. And for people on Zoom, I'm just kind of pointing to a slope on my hand. And then we measured somewhere else another year. We haven't changed, but that's DH, not, or DHDX, not DHDT.
So it's just to distinguish.
Exactly.
Yep.
Yep.
That's quite a sizable development team. Who at NASA funded that? Was it out of the project?
This is out of the mission, yeah.
Mission.
Yeah.
Cool.
Yeah, and it's from the Project Science Office and then collaborating with NSIDC. And the nice thing is NSIDC's timeline to transition to S3 was going to be this year, but the Project Science Office, with enough prodding from our team, got that moved up about 1.5 years. And so we got a lot of data on S3 earlier than it would have been. As for our project, if we were trying to host the entire S3 archive, as Eric just said, that would have gone through our budget very, very fast. And so for our initial stages, when Hannah first started working, we could only host like small regions, as we didn't have the money in to try to host the entire archive. And it would have taken forever to go from one to the other. Yeah.
Have you figured out rules if people use your tool? Do they acknowledge it in publications, or are there guidelines in place, or is that still under development?
Yeah, we have a DOI and a JOS manuscript, both of which are citable. As with any paper and work, it's the responsibility of the authors to acknowledge the work that they have done. Data citations are still kind of in the Wild West on how people do it. But we do provide a DOI for the actual surface, and we have in our documentation under citations, and please, if you use SlideRule in your work, Slide has this. And so that's part of having, well-written documentation, is that if people want to use your services, as hey, please do, but please acknowledge the work that you did. And that goes with all open science work on that. If you are in the open, you should be acknowledged for the work that you're doing, because it takes a lot to maintain software, it takes a lot to maintain documentation. You have to interact with people that either run into bugs or run into features. And so your work that you do with it needs to be acknowledged, because can be quite substantial.
I was curious, because you said you can literally pull out your phone and try to SlideRule on it. I was wondering if there's an app or you have to like post it to your notebook on your phone.
No, so there's a web demo, and so it's all compute is on our side, and then all you get is the time series and the photon, or not, you can look at the photon, but the 7 heights. And so your phone is just getting these interactive maps where you can zoom around, and you can draw your polygons on where you want to be. And so it's not, you're not running Python on your phone, you're just getting the data back that you can visualize.
You download the data from your phone?
No.
I just like the idea of drawing my phone down.
Yeah, we are wanting to do export, we just don't have it on the web anymore right now. Probably because we don't want to roll someone's phone. But yeah, you can, at the very least, you can save the plots like that.
Any?
Interesting.
Just a quick question about ocean products. So is there an ocean wave product? I don't know, it's subsurface, but.
So there is an ocean product, it is averaged over 7 kilometers. They're trying to average out the effects of waves. That's the main thing that they're trying to go for is sea level rise. However, there are smaller segments within that you can see the individual waves for. So there is an ocean product, but for iceberg use, it's similar to the CS product. They eliminate anything that's too far away from the geoid or sea surface height. And so for some uses, there are things that are actually floating on the ocean, it just is a giant hole. Which eventually could be somehow to detect, however, we have to figure out if it was a cloud that prevented it from sitting there, if it's the free hole.
Another subsurface, like in water,
There's work that is being done for coastal reasons, because it is marine and it does penetrate, so you can't see the symmetry. And then there's someone in Oregon that is trying to look at biomass by putting some sort of figuring out how much photon returns is in the lunar surface. I'm not 100% familiar with the work, but I know that there is someone that is trying to look at like algae.
Which is very hard.
Yeah. But yeah, it's green, so it penetrates into water, which is cool for bathymetry applications in both ice lakes and coastal.
Of course, study to the, when you look at sea level and subsidence, that can be very useful too. Any other question?
Is there a follow-on mission?
For ICEF3,
Yeah.
it needs to be recompeted. And so ICEF2 was mandated from headquarters, but ICEF3 will go through the normal competition process for missions. There are
A place in the Earth Science Observatory?
Yeah, probably an ELS or ESM, whatever one it is. Yeah, and so whatever is the next generation laser altimeter will be in the open competed realm.
I'm gonna talk next to you because it's like,
Okay.
I'm sorry, it's like, I did the microphone. So if people on the Zoom wanted to put questions, please put questions in the chat and I'm gonna read them. Any other question? Okay, well, thank you, Tyler.
Yes,
Great.
thanks for having me, guys.